This is our aluminum hammer lab where we start off with a CAD drawing and we finish with a completed aluminum hammer. This is our completed CAD drawing of the hammer, complete with tolerances. This is our completed aluminum hammer on top of the CAD drawing, which was the basis for its construction. This is a small metal cutting bandsaw in the down position. It runs at about 1/10 the speed of a wood cutting bandsaw.
This saw is now in the loading position for cutting the 1¼ inch aluminum rod that we want to cut off to a 3-inch length. I'm going to now position it in the cutting position. This is the loading position, up in the air. It now goes in the cutting position. There's a spring mechanism on the side, sometimes they're hydraulic, that keeps the saw in balance so it doesn't have too much weight on the blade. Now, one of the important parts is to make sure that you cut the piece slightly longer than what you want. And you would position the machinist scale alongside the material and up to this touching the saw blade. I'm going to do a little bit of a close-up on that right now.
Are you taping down there?
Yeah. Okay, as you can see, when the saw blade cuts, the piece should be a little bit over, about 1/16 of an inch in this case, the length that we want. Now you would say to yourself, why do you want it oversized? If you want a 3-inch piece, why are you cutting it to 3 1/16? There are two reasons. One is that the saw may cut slightly crooked on this side and subsequent cuts on this side. For instance, if it cuts crook here, when I slide it out, now it'll be crooked on both sides. So you really have to cut it a little bit long in order to be able to face it off in the lathe to get it to be the perfectly length that you wanted. Now, our hammer doesn't really need to have exactly a 3-inch length. It could be a few thousandths over or a few thousandths under, but we do need to have a smooth surface. So we're going to put it in the lathe after we finish doing this cut, and we're going to smooth it out. And as we smooth it out, meaning we're going to cut this piece off here a little bit and trim this piece off here a little bit, it's going to become a little bit shorter, and that's why we're cutting it oversized right now. Let me check and see what it looks like, and then we'll watch it do the cutting. Okay, we're about ready to look at it do the cutting. I'm picking it up slightly to get it the on-off switch. It is now in the running position. It is now running, and I'm going to gently put the saw blade down, and you can hear it cutting the material, the aluminum. You can even see it cutting the material, the aluminum. fighting a little bit with the tripod right now. Okay. Now you can actually see it cutting the material and doing a nice job on it, far faster than you could possibly do it by hand. Now, in a production operation or in a regular machine shop, we may have coolant being squirted on this little hose type of thing. It keeps the blade cooler and lasts longer, and it makes it faster to cut. However, those coolant operations are not necessary, and in a lot of shops, they may be more of an annoyance. I'm holding it right now because it's about ready to sound it, it's about ready to cut it off, and I don't want it to fall on the floor. Okay, so cut it off, and as you notice, the saw was shut off after cut off. This is another cut of a smaller piece, but from a different angle so you can see what it looks like. You can see the saw blade resting on top of the material right now, the aluminum, and it's only a skinny piece, but it was for demonstration purposes so that you can see the way the saw cuts through it and the way the saw chips actually, would be pulled out of the cutting area. There we go. Now this is a dry cut, and we also have to keep in mind that various grades of aluminum behave differently when they're being machined. Some grades of aluminum are very gummy and they have a tendency to get stuck in the saw blade. This one does not. It cleans out very nicely, which makes it a nice easy easy alloy to work with. Of course, easy alloy to work with does not necessarily mean it is the best alloy for the particular job that you have in mind. As you can see, this is way faster than even thinking about doing it by hand. At the end of the cut, you may even hear the difference in the sound being made by the saw as the piece of metal gets thinner and thinner. It has a tendency to change the pitch and tone of the sounds coming out of the saw. Not yet. Now. Okay, that was it.
This is the lathe we'll be using for our hammerhead and handle demonstrations. It is a small to medium-sized industrial grade lathe, which are still being sold today, which basically have the same features as this one does. You're dealing with a very basic machine tool and a very durable machine tool. This machine is a World War II veteran. It was made in 1943, which makes it 78 years old as of this video, and it still runs perfectly. We're now going to look at the various parts of the lathe, and I'll be describing to you what they do. This is the chuck for the lathe, kind of like a vise, and it holds on to whatever workpiece you need to be operating on. This is a 3-jaw chuck. You can see the 3 components on it, and it is for round objects. And there are also 4-jaw chucks for irregular shaped objects, and there's ways to make them work like that. This is the power head of the lathe. It rotates the lathe chuck and the piece that's being worked on so that the tooling can machine it to whatever configuration that you need to operate on. This particular headstock, which is what it's called, is a double reduction pulley drive combined with a double reduction gear drive. As such, it can go from 30 RPM to 1500 RPM. That makes it very versatile. The lower RPMs actually multiply the torque so that it can really take heavy cuts or move big objects that are large diameters. This is the carriage of the lathe. It moves left and right. It contains many components that have a lot of different functions, and we'll describe them as we need them. But this is where the cutting action occurs. The large handle on the lower left side moves the entire mechanism to the left and to the right so that it can perform longitudinal cutting. This is the handle that controls the in and out movement of the cutting tool if you're doing it manually. There are ways of doing it power, which we'll be discussing in a few moments. This is the compound rest. In this view, it will be moving left or right, but it can be pivoted to cut at any angle that is needed to be made for your operation. This is the cutting tool on the lathe. You can think of it as a sculptor's chisel in that it removes the unwanted material from the workpiece. It is made of many different alloys, and it is extremely hard and has to be harder than the material being machined. This is the set of power controls for in and out feed and left and right feed. It is not necessary to use them because you can do those operations by hand with the regular manual handles, but it does provide for a much smoother operation when you can use them. These controls enable us to engage and disengage thread cutting operations at the appropriate time when you are making some kind of threading operation. This is a close-up view of the actual cutting tool in the quick change tool post and tool post holder. This is the quick change gearbox. It allows you instant access to 48 different threads per inch or feeds on the lathe. This is a close-up on the gearbox, and you may be able to see the various speeds and feeds that you can do on this particular lathe with it. This is a stack of gears I have on the shelf in the shop. With this stack of gears attached to the back end of the lathe, those 48 threading operations or threading feed rates can be changed into several thousand feed rates, including all metric feed rates. This is the tailstock on the lathe, but in our operations with this hammerhead, we will not be using it today. But it is used for drilling and holding a piece with us between centers. But we will not be using it. On the left side of this tailstock, you can see a drill chuck. In this view, we see the saw cut hammerhead in the lathe chuck. We also see the cover open so that I can adjust the speeds. When adjusting the speeds, the lathe must be stopped. There is no other way to do it on this type of lathe.
Okay, so here we go. High speed on the lathe. And as you can see, it takes a while for it to wind itself down. Now we're going to set it at the slowest speed on the lathe. Here is my 30 RPM low speed. Now this is really nice speed when you're trying to do threading and other tough operations. Could be tough metal or it could be a delicate machining operation, but this allows you to see what's going on. Alright, I'm going to now set it up for the facing operation. Okay, before we do anything, first though, on facing this off, we're going to set this in a normal position so that I can cut this piece to a precise length, which means this piece here, which is called the compound rest, has to be rotated 90 degrees so that this handle can be used to control the depth of cut. This handle will be used to control the cross feed or cross cut operation. So, indicators here that are going to tell me when it's exactly parallel with the ways. And okay, right now we're about ready to start running the lathe. First thing I'm going to do is touch the tool bit here up against a piece of aluminum to get a reference point of how close I am. I'm going to now turn this thing about 15 thousandths, that much, and that will allow me to take off 15 thousandths from the spot where I bumped it. Now depending on how crooked it is, it may or may not be 15 thousandths all over, but it now will be flat all over. So let's go and do that. And also at this point in time, I'm going to use the manual feed, which means I'm going to be using the standard handle in the front that we discussed, and we're just going to feed it in by hand, nice and smoothly. Okay, we finished that cut. We can move it out. And what I'm going to do now is the edge here is fairly sharp, and we don't want it to be sharp, so I'm going to grab a small file and I'm going to file it off nice and smooth. Or around the corner off, actually. Holding both ends of the file, left hand and right hand. I'm going in and rotating. Going in and rotating, going in and rotating. This is going to give me a round little bevel on the part here. Sometimes you want it to be sharp, sometimes you want it to not be a sharp issue. It's, how you finish this is unlimited possibilities. Even this piece here, where we fit it straight across, a standard hammer has just a little bit of a crowning to it. That is very difficult to do on a manual lathe. On a CNC lathe, yes, it's possible. On a manual lathe, you can do it also, but you have to build a cam to go on there. We do have a cam to do that on our lathe at the university. So right now, I've got to turn this around. We're going to finish off the other side like this. We're going to measure it to see how long it is, and then decide how much we got to take off to get our hammerhead 3 inches plus or minus about 5/1000ths of an inch, which will be standard general purpose machine shop standards. Okay, so let us take this piece out, flip it, put it back in, bring the cutter up to the piece like we did before. Back it out a bit. Turn it another 15 thousandths. And now we're going to face off this side. again, a little bit of a round off file just to get it out of the way. There's a particular technique for the filing, which we'll get into when we get into the shop. There's no point in talking about it right now. But there's safety issues are very important to follow. All right, so now we have this piece, and it is now smooth on both sides, but I don't know how long it is. Let me measure how long it is, and then we'll see what we need to take off of this piece in order to get it to be the right length that we want. Now the piece is flipped around. I've measured it, and it's 0.010 of an inch over 3 inches. And we're going to try and make it as close to 3 as possible in one cut. It's a 5,000, that will be, I have to feed it in this direction, 0.010 of an inch. If I'm 0.010 of an inch over, we'll do that with the dial over here. This case, I'm going to do it with a power feed so you can see the cutting operation from a different angle. All right, so now I've got to engage the power feed mechanism here. We bring the cutter up to the piece till it touches, drag it out, move it in 0.010 of an inch or so, turn it on. Hear the racket from the power feed mechanism. We're going to now engage the clutch down here. Oh. We bring it in a little closer. And we engage the power feed mechanism. We're making our 0.010 of an inch deep cut. On power feed. Okay, we got to the center. I disengage the power feed, crank it away. And we're going to remove it and measure it to see where we are. Now, before I do that, I'm actually going to file it, but I didn't want to get in the way of the camera. All right, so that's right now where we're going to stop.
Here we see a digital caliper indicating that the actual length we machined is a 0.005 of an inch less than 3 inches, well within what we would want it to be. But that number itself is subject to a little debate because we don't know when the calipers were calibrated, what the temperature of the metal is, and other factors. But it clearly indicates that we're well within the limits that are established on the drawing. In this picture and in the ones that follow, we're going to take a look at the vertical milling machine that we have here and its various parts. It is important to remember that while the vertical milling machine looks like a drill press, it is in fact a very different machine. It has a much heavier quill, the part that goes up and down, heavier bearings, a much stiffer column behind it. It has an XY table securely mounted and integrated as part of the machine, a vise that's bolted to the table. It has handles that can control table movements to thousandths of an inch, and in many other ways is totally different from a milling machine. It can, the milling machine, however, can act as a drill press, but not the other way around in most situations. We'll be discussing them as we see the various parts highlighted in the following pictures. In this picture, we see a drill chuck mounted in the milling machine, and it is holding on to a wiggler type of edge finder so that the position of the head relative to the vise and the material in it can be located with great precision. In this picture, we see a milling cutter that we're going to be using to machine the flat surface on the hammer head itself. In this picture, we see the drill mounted in the drill chuck that will be used to make the hole in the hammerhead that we'll be able to then insert a tap into and create the threads that will be needed for the hammerhead handle to screw into. In this picture, we see a red arrow indicating that the quill can go up and down, holding the tool in it while it is doing the job that we are planning on it doing. But it can strictly move up and down while it is rotating. In this picture, we see the handle that can move the quill up and down with great speed, but not necessarily great precision. That is for another dial on the machine. To make it go down, it will be turned counterclockwise here. In this picture, we see a dial which, when it is engaged, can move the quill up and down with great precision, specifically to 1/1000th of an inch, or possibly even left, depending on how good you are at finessing the dials. In this picture, we are recognizing that the head itself can move up and down about a foot with the help of a geared handle on the opposite side of the machine that is not visible. When that is used, however, the head can spin freely and all position indicators have to be reset. In this picture, we can see by the arrows the table can be moved left and right, and while moving it, it moves the vise and the part that is being machined, and that is how the machining on the part is affected by moving the table and components left and right, in and out. These arrows are pointing to the handles that, when rotated, actually move the table in, out, left, or right. In this picture, we are getting a close-up on the dials that indicate the position of the table, left, right, in, or out, with each line on the dial representing 1/1000th of an inch. In this picture, we see the machine from another view with an edge finder mounted in the chuck, and it's about ready to begin the edge finding operation. This is another overall view of the edge finder about ready to do its job. This is a much closer view of the edge finder about ready to touch the workpiece to find out and position the workpiece with great precision. This is what it looks like when the edge finder has just passed the edge, and it gets kicked out of position. At this point, the quill must be withdrawn quickly to prevent damaging the edge finder or the piece.
We are now going to tap the blind hole, meaning that it's not a through hole, you can't see through the hole. We're going to tap the blind hole with a standard type of tap and a standard type of hand tap. This would be used by machinists for blind holes, and it would be used for mechanics and general purpose home or small shop use. In fact, it's the most popular type of set, and this set actually came from the original Sears store. Haven't used it all that much because I've used other ones, but anyway, it's in very, very good shape, but it is your classics tap that if you don't specify something else, this is what you're going to wind up with. So if you want a special tap, you got to tell the vendor you want a special tap. Otherwise, this is the type you'll wind up getting, and it is very good. Its prime issue is that the chips are going to be coming in here, and there's not a lot of room for a spiral chip, so you have to back it up every once in a while to break the chip that's been caused. We'll probably be going in about a full turn, and then we'll back off a quarter of a turn as we do it. So now we're going to hold it as perpendicular as we possibly can, and we're going to take about a turn, especially at the beginning when it's starting. It's a bit tricky to get done right. Okay, we're getting there now. All right, so we got it. Besides the general rule of thumb of going in about a turn before you back out a quarter of a turn, I'm feeling the resistance in it. Now, I could see inside the hole there, a nice chip is forming, and it is starting to clog up the hole. So I'm going to back off a quarter of a turn. It's going to break that chip, and it's going to fall to the bottom of the hole. And I could feel it actually snap the chip that was there. Okay, I'm going to back it off again. And right there, you'll see the jump and the tap handle when it actually breaks the chip that's been forming and clears it to the bottom of the hole. There it is, goes right now. Now sometimes, depending on how big the chips are, the size of the hole and stuff like that, you may actually have to take the tap out, take the piece out of the vise, turn it upside down, knock the stuff out of it, and then continue making the tap. In fact, I am thinking that we might have to do this here because of the size of the chips are pretty big. This is being a 1/2 inch 13. There's a substantial chunk of metal that's being peeled off. It's making an interesting noise that I could hear, but I doubt if you could hear it. The noise is actually peeling the metal. I'm going to, right now, withdraw the tap, take the material out of here, just tap it on here, and knock the material that's accumulating in the bottom of the hole out. Got a good sized length here in the chip, and it's in there. Pretty good, pretty good. But I'm going to clean the tap out in a moment, and right now I'm going to knock all of the debris out of the hole and off the top of the chip. I think you should be able to see this. Let me all right, so we got a nice little picture there, I think. I'll tighten this back up again. I'm looking in the hole, by the way, and it looks as if we're fairly close to the bottom of the hole. So we made a lot of progress because the threads per inch was so coarse that you go in very quickly. All right, so let's go down a little bit more, see what happens. Should be able to go in maybe another turn or two, That's it. All right. Okay, so that's what we've got. Now I'm going to bring the camera over here and I'll show you what the inside of the hole looks like. And not surprising, but it's interesting to look at.
All right. The hammerhead, it's still in the vise or locked in the vise, and we now have a very good view of the threads that have been formed. We can actually see the threads going down into the bottom of the hole. We could see the smooth bottom of the hole, and we could see some chip debris at the top of the hole. Uh, in addition to that, we can also see very nicely here the flat spot that is being provided for the nut to lock the hammer handle up against the hammer head to keep everything from loosening up.
Right now, we're going to be threading the end of the hammer handle that goes into the hammer head. This is the die. We're going to be using it as a die as opposed to a lathe cutting it with single point threading. Dies are very good. They're very easy. You don't need especially a lot of skill, and they're very handy. Very common in a lot of machine shops, garages, gas stations, home shops. So we're going to be doing this, and it's going to have a lot of the similar characteristics of the tapping that we did, in that you're going to be going forward, and then we may go backwards depending on how difficult it gets. But there is a lot of room in here for the chips to form, so it may not be necessary on this particular size. They have a top and a bottom side, and then this one specifically says start from this side. So this side goes down. The tricky part about this one is keeping it as close to perpendicular to the axis of the rod as you possibly can. It is a little bit tricky to do. Now, I took a skim cut on the lathe on this just to make it a little bit easier and to do a little bit less wear on the die itself. You got to fight to get it on. There's no doubt about that. And you want to really try to get it on straight, because it has a tendency, especially if you try to do it a longer distance, to wobble as you get on, and then it winds up being crooked and the hammerhead isn't perpendicular to the handle, which is not a good idea. Yeah, we definitely need to break this one. In fact, I'm going to even put a little bit of extra lubricant on it, cutting fluid. I had put some on there already, but it's pretty tight, so I'm going to put some more on. Well, that's a whole lot better. This is a little bit slippery right now, so what I'm going to do is I'm going to take it out of here because it's spinning in the vise, and I'm going to stick it in the lathe chuck. That'll grab it a little bit tighter, and then we'll do it on the lathe, which will be holding it nice and steady. All right, so let me just pause the video for a second while I put it in the lathe.
After I put it in the lathe chuck, I tried using the die handle and the die again, but it's kept slipping. Basically, my die is very old and pretty dull, so I'm going to give up on using the die, and I'm going to use single point threading on the lathe to finish threading the hammerhead. This is the setup on the lathe for single point threading. This is a picture of the hammerhead handle incomplete in the lathe and with the thread cutting tool just to the right of it and getting ready to be prepared to be used.
We've run into a bit of difficulty with the die, so I'm going to be doing single point threading on the lathe. We just finished looking at the setup. I lined up the threads with the prior partially cut threads, and we're now cutting the threads to full length, but at a step at a time. And we're again doing a second cut. This kind of an operation could take 5, 6, 7 cuts depending on what's going on, because you're removing a little bit at a time. You can see the nice chip being peeled off even though it's a little bit.
We have now finished machining all the parts. I've taken the handle, cleaned it off, threaded a nut onto it, and then threaded the handle into the hammerhead and set the nut up against the hammerhead to keep it from twisting. And I've put it on top of the blueprint drawing so that we can see the project that we've created on top of the blueprint that we used to create this project.